Since we are videotaping, if anybody doesn't want their face on, then the back door might be a better choice than the front door. But that's just my only. That's just a blanket warning that I should have given in the first lecture. But we are recording and throwing them on YouTube. Yeah. Okay. So last time I tried to motivate what I think control should be. You have a vector field. You have a little bit of control authority over that vector field, and you're trying to basically change the vector field to do your bidding, right? So we did it last time on the pendulum. Right, and we started drawing the vector field of the pendulum, which I could plot theta versus theta dot. The equations of motion were a second order system. And if we started plotting those equations of motion, the vector field for those equations of motion, we had this plot that came out, which had the eyeball looking thing in the phase portrait, and it would repeat. This is for B equals 0 and U equals 0. Right, and we'd have orbits that were roughly circles around here. Sorry for the bad one there. And they would repeat, right? Get my color chart. And this was a fixed point that was stable, at least in the sense of Lyapunov, even when the system was undamped and uncontrolled. As soon as damping is positive, then the trajectories would spiral into the origin and becomes stable in all of the senses we talked about last time. And this was an unstable fixed point over here, and every 2 pi, right? And then we talked right at the end about saying this is what you do as a control engineer, I guess. You have just a little bit of control. You actually don't get to change the direction, the horizontal component of the vectors, because that is just theta dot. Right, the x component of this is theta dot, and the y component is theta double dot. The control input you have, your torque, affects accelerations, but takes time to affect velocities. Okay, so you get to do a little bit of work here by changing u, plus or minus u, moves that up or down. And the goal is, for instance, on the pendulum, the fun thing to do is to try to take this unstable fixed point, which is the one at the top, and make it a stable fixed point. Okay? So what tools do we have to do that? I mean, we're going to try to give some better tools today. The only idea so far we've really given you so far is feedback linearization. And just to make it clear, the feedback linearization approach to this, the controller would be very simple. So what might I write as my control policy for you that would turn this into the stable fixed point?
2 mgl sine theta.
Awesome.
Or 2 mgl sine theta, sorry.
Yep. 2 mgl sine theta would do the trick. If I stuck that in here, the result would be ml squared theta double dot plus b theta dot minus mgl sine theta. So you basically have inverted gravity. Okay? And that's, so that would be equivalent to erasing this vector field and drawing the eyeball over here, which you are able to do because all the x components are the same. You've just changed the y components. Okay, but you've moved that whole thing over here. And you could argue that there's nothing wrong with that. The algebra's good. The practical reason why you might want to do that is that the first practical reason is that it requires potentially large u's, even for relatively small, you don't have to be at high velocities, as there's no velocity term. This, I guess, sine theta is bounded by 1, so it's going to be up to 2 mgl, which is relatively a large torque for a pendulum. So, here's a harder question. How would you stabilize the unstable fixed point? If I give you a constraint, a torque limit, let's say it's mgl over 4. Okay? Suddenly that takes the easy answer, the algebra answers, and it just makes them not work at all. And actually, the problem gets really, really hard really fast. So if I just applied that controller and asked my motor to do something, but it just saturated, we might write that as, for instance, if I were to apply the saturated to mgl sine theta, which is saturated at mgl over 4. That's just shorthand to say that I'm going to write in all the cases here, right? I want to just saturate my controller right up there. My sat function is just use x until it hits the limits and then hit on the limits. If you were to apply this saturated controller, then we already saw what it was going to do even by our overdamped analysis of the pendulum, right? So if I apply only mgl over 4, then it won't have fixed the vector field. In fact, it'll get stuck somewhere over here. Your new fixed point is going to be, fighting against gravity, but I need MGL to get up to here in the overdamped case, right? So it's going to be stuck going like this, right? So it's not going to manage to swing itself all the way up to the top. You can imagine, though, that there's pretty simple, physical. You could come up with your physical intuition controllers that will use this and accomplish the task. They're going to take the form, they're going to look more like someone pumping energy, like pumping a swing, right? You pump a little bit of energy, you could with very little torque. In fact, the only torque you really need is you need enough to overcome damping. If you can put in enough energy in to overcome the damping, then you can push just a little bit harder, it'll pump up, pump, and eventually swing up and balance, okay? So for the pendulum, there is a mechanical intuition that could give us the controller. But actually, I want to make sure we can solve this in a more general way, because we want to solve more than pendulum in the class. And today is the first class that the first sort of algorithm, numerical algorithm we're going to start giving to make sure we can solve at least that problem, but many more. Okay, so the way we're going to do that is we're going to invoke the power of optimization. More generally, in fact, it's really, we're just barely starting with the tools of optimization today, but and this is an idea that we're going to use over and over throughout the class with increasingly sophisticated tools for optimization in order to scale to more complicated problems. But we're going to get by with a very simple algorithm today. And the way that you do this is that somehow the problem is if you are given a trajectory, so if you watch the system behave, and in this case, a trajectory, I will repeatedly use this shorthand to mean for all t over some relevant interval in, let's say, 0 to some potentially infinite interval x of t. Okay, I'll use this to mean the entire trajectory of x. And a trajectory of u. Once I'm given this, I need to assign a score. You know, a scalar value. So that's like, you know, watching the Olympics and you watch someone do a backflip and the judges hold up a number. You know, it's roughly what we want to do. Is for every trajectory we observe of the system, we need to give it a scalar value. And then we can formulate the control design as trying to maximize that scalar value. And depending on the scoring function that you've chosen, it could be, you might have made the work harder for yourself to optimize that or easier for yourself to optimize that. The other tool from optimization is, in addition to assigning some objectives, we can also use constraints. Which says that I'm going to disqualify any trajectory, for instance, that doesn't satisfy some constraint. Examples that we're going to see, for instance, are we could have for all t, my ut must be less than or equal to 1. That's an input constraint. You could also have a state constraint, like for instance, an interesting one would be maybe I'd like to arrive at the goal in some finite time. I'll call it t final. I'd like to be at the goal. And we're going to be able to use optimization algorithms that can take this kind of constraint on, you know, inequality, equality, inputs, states, any combinations of the two. Okay? And our goal is to find a policy which we will get pretty far by thinking of it as a function of time potentially, state potentially. But we're going to learn, we want to find a function that optimizes that score. So there's this funny thing, which is that control theorists call these controllers. Reinforcement learning people call these policies. I find them sort of a mixture of the two. The other thing is reinforcement learning people maximize reward and control people minimize cost. Maybe that's a statement about the types of people that work on the problems, I don't know. But I tend to use cost, and I'll try to use policy consistently throughout. Okay? So we'd like to optimize that cost. Ideally, we'd like to optimize it for all t and x. But we'll find later that we might have to make some compromises and say, let's say, initial x's. We might have to make some compromises later where we say some x's are more important than other x's, right? There's some parts of state space that matter more to me than others. And here's the thing, so it normally always is going to involve some sort of a numeric solution, right? Some numerical algorithms, approximations come in pretty fast. But there are a few, special cases where we do know analytical solutions to the optimal control problem. And so I want to do, at least one of those so you can see the power of that and have some clarity from that, I hope. Right, so the classical example, which is very relevant for swinging up a pendulum, but has a closed form solution, is the double integrator minimum time problem. See that. Okay, so the dynamics of the system are just Q double dot equals U. It's a double integrator. Q will be the double integral of U. And we're going to say that it's input limited. And if you want a physical motivation, a physical connection for this, which it always helps me think about it. Think of it as a unit mass brick on ice. We have a force being applied in the horizontal plane. There's some zero here, okay? And the goal is to drive this brick to the origin and stop at the origin. Is to achieve this state and stay there in the minimum possible time. So what do you think the optimal policy for that's going to be? If you're driving along, you're in some particular state that is not the origin, what do you do to get to the origin as fast as possible? Yeah?
Accelerate it, decelerate as far as you can.
Exactly. You're going to hit the gas until you're at some critical point, but you're going to have your foot to the floor the whole time until you're at some critical point where you have to hit the brakes on full on, and try to come to rest come to rest exactly at the origin, right? Anything else is going to take longer. You're either exactly where you want to be and are slamming on the brakes, or you're accelerating to get to the point where you need to slam on the brakes, right? It's often called the bang-bang controller. Okay, so it's accelerate full throttle. Then slam on the brakes. And it's really easy to see this in the phase portrait. So let's do that real quick. So Q double dot equals U. Let's understand the case where we're slamming on the brakes. Okay, so and it depends whether it's accelerating or on the brakes. I guess depends on which direction or which side of the origin you're at. But let's at least understand what happens when I'm pushing full on in the negative direction. Okay, this is about the only differential equation I have in class that I'm going to be able to integrate for you, right? Right, so it's Q dot 0 plus T, I guess minus T if it's -1 here. And then, let me write this more carefully here. Q dot T, and Q of T is Q of T's, Q of 0 plus T, Q dot 0 minus 1/2 T squared. Right? So what does that look like in the phase portrait? Q versus Q dot. Well, if I start even at 0, 0, then I'm going to have this negative T. It's a parabolic curve that goes out like this, right? And if I started with positive, that turns out to be that whole curve is a feasible orbit given I've got U equals -1. And in fact, no matter where I start here, I'm going to take this parabolic, I'm going to have this parabolic solution. It's just a function of my initial conditions, but so this is what the phase portrait of that system looks like when I'm got U equals -1. Yeah? When I've got U equals +1, it's going to be almost the same, but I got a positive here, and I have these curves going off in the positive direction. And in fact, it's going to look like this. Okay, that's the U equals +1 curves. So the bang bang controller, the way I can decide now which of those two actions I want to be applying is I look where I am in this space. How do I get here as fast as possible? Well, if I'm here, I'm going to ride this acceleration curve up until I hit this. This is a special one, right? This is the one that intercepts the origin. This is I'm hitting the brakes and coming to a screeching halt exactly at the origin. So your job is to get to that curve as fast as possible and then ride it in, right? And nothing else matters. No matter where you are, you go there. If you overshoot it just a little bit, then really you just have to keep going until you hit this curve and then ride it in. Right? So the optimal policy is exactly, so we know that right here, this is now the optimal policy. This is U equals -1. We know that's optimal. There's nothing better to do than to go there. Over here, we know the optimal policy is U equals +1. Nothing better that I could do there. And over here, everywhere else, I want to be applying this same controller, because it's going to be the controller that gets me to that line as fast as possible. So everywhere else here, I want to be doing U equals +1. And over here, everywhere over here, I want to be applying u equals -1, because that's going to get me to this curve as fast as possible, right? So that, it's actually relatively hard to prove that that's optimal. We'll work back to it to actually give you a sufficiency theorem for it. Even the normal sufficiency theorem doesn't work because it's a discontinuous policy. So it's kind of annoying to prove that it's optimal, but it's optimal, trust me. Your instincts told you so, I'm confirming that. Okay, and it's beautiful and it's simple. And the question I want to ask is, if we didn't have that intuition, if we didn't have that guess, how would we have written an algorithm to come up with that policy, right? I want to get back a numerical algorithm that's going to produce that. And I'd like to have my numerical algorithm do the same thing, but work also on the pendulum or whatever other system we're interested in. Is that clear? All right, so minimum time was just one particular choice of a cost function that I could have picked for that problem. It's the famous one, that's why I picked it, of course, but I also picked it because it connects very naturally with the types of search algorithms that people know in the discrete world as graph search, okay? So minimum time is closely related to a shortest path problem on a graph. So that's my hook. We're gonna try to use shortest path algorithms to solve the more general version of that. So if I have some graph, draw whatever you want here, and I've got some goal, and I want to find what is the shortest path from any given state to the goal, then there's a whole family of algorithms that will tell you how to do that. You've probably, if you're taking a computer science course on search, right, there's lots of search algorithms to do it. If you want to solve it for every initial condition simultaneously, instead of just solving for a particular one, then the way that people solve that is with dynamic programming, okay? Particular recursive algorithm that's very good at solving that for all initial conditions. Okay, so the picture I want you to have to apply this to the double integrator is that on the phase portrait, we're going to approximate the dynamics of the double integrator by loading up a graph on top of the state space, right? We're going to put an edge between two nodes if there's a control decision U that would get me from this place to this place. So which happens almost never, by the way, right? So like, right, that should you'd have to get very lucky to land exactly on one of the other nodes. So I'm going to brush that detail under the rug for a second. We'll show you the way to handle those in a minute, or next lecture, really. But roughly speaking, you could say if I land close to that node, I'm going to draw a line to that node. But for instance, there are no edges up and down here. We'll do that one. But up here, for instance, does not connect to here. It certainly doesn't connect to this guy over here, right? And then the minimum time problem for the double integrator just becomes a shortest path problem on this graph, approximately. And if I can make that graph dense enough, then you'd expect it to get better and better numerical solution, right? More generally, if I have different cost functions, I could also do weighted shortest distance, right? If I put different costs on different edges, there's the weighted shortest path problem, and we'll use that too. Okay. So I'm going to try to be careful. I'll use a different letter when I'm talking about discrete states versus continuous states, discrete actions versus continuous actions. I'll try to be careful about that. So I cut my finger open right on the part where apparently I use constantly to turn pieces of paper and to write on chalkboards. That's kind of annoying.
There's a question in there.
Oh, sure. Thanks.
I just wanted to, are we only looking to put edges between nodes that are kind of like close to each other in space, or like adjacent in some sense? I mean, could you have an edge that goes from like the bottom left all the way to the top right?
It's not whether they're adjacent in space.
Yeah.
It's whether I can get there, whether my dynamics permit me to get there in a step.
But I'm asking what's a step? I mean, when you're, would you even consider drawing an edge from a node down there to a node up there?
Good. So I'm discretizing three things, which I'm, so I'm discretizing state by tessellating it this way. I'm discretizing my actions in a moment because I have only a finite number of edges coming out.
Right.
I'm also discretizing time. So I have to pick what is my canonical time step.
So whether or not there's a control that gets you from A to B within this.
Within a single time step,
Okay.
which is typically a small number, and the smaller it is, the better you'd expect it to be an approximation of the continuous time.
Okay.
Good question. So I want discrete states. My continuous states are X, but I'm going to have discrete states now. I'll call them S, and there's some finite collection of them, which is a bigger S. I have discrete actions. I'll call them A, which is there's a discrete set of them in the family A. I have discrete, this is just me not writing discrete every time. I have discrete dynamics, where I always wrote x dot equals f of xu. Today we'll do Sn plus 1, so this is now a discrete time. This is my dynamics from wherever I am at time n, and whatever action I've taken at time n. Okay. I'm going to write my cost function. Remember, our goal for optimization is to specify some cost, and I'm going to write it in parts. I'll say the one step cost is G, could be a function of S and A. It's a scalar. And my total cost along a trajectory will be, I'm going to just add these up. And over potentially an interval, over some interval, it could be infinite or it could be finite. I'll stick with infinite for now, but every time you see that, you should think, you're going to make sure that thing converges, if it doesn't go off to infinity, and I'll try to convince you that we'll be okay today, okay? So this is an example of what I said before. I watch a trajectory, right? Maybe I watch it forever, but if so I better get somewhere so I know that it's going to have some property. And at the end, I can assign a total score. Right? And this is exactly the formulation that you'd want in your graph search problem if you had a weighted graph, right? So if I had edge weights here, maybe this costs 2, and this costs 3, and this costs 4, and this costs 16, whatever, then this could be my one-step cost, and the total path cost is just the sum. All right, so this is a key idea. This additive cost. Right, even in the continuous time, we're gonna see it as integrals from 0 to infinity, let's say, of g of x, t, ut, dt. We're gonna see this structure over and over again. The reason is because it adds so much structure to the problem that it makes it way more accessible for control design. Okay, having this structure, and you'll see that in a minute, it gives a recursive structure to the long-term solutions that we're going to exploit immediately. And in general, it's the most common form for writing out the long-term cost functions. It's also fairly expressive. You might see this and think that's pretty frustrating, but for instance, minimum time problems can be written with additive cost. How would you choose G for the minimum time problem?
This one is the one that you got to go through. Yeah.
Awesome, yeah. It's 1 if S is not equal S goal, and 0 otherwise. Right? Oftentimes we'll see things that are smoother functions. Another example that we'll see a lot is a quadratic cost. Makes more sense to write it in continuous, but you could do it on the discrete. You might see, for instance, x transpose x, something like x squared plus u squared. This would be, I want to score myself based on how far I am from the goal, right? I'll put rings of cost. I'll penalize myself from being away from the goal. This goes to 0 at the goal, right? And I'll penalize myself for using big control forces. That would tend to drive my control forces. This is just another common example that we'll use a lot. Okay, so it's pretty expressive to have these additive costs, and it fits right into the graph search picture. So when is this thing going to converge if I use, let's say, the minimum time cost? Oh, sorry, yeah?
I don't understand well why the function v of s, a is a minimum time case.
This one?
Yeah.
So once I'm at the goal, I accrue 0 cost. And this is, just think of it as a graph search where I put the edge weight as 1 everywhere. So every time, I'm going to take one edge, and I'm going to penalize myself 1. So it's going to accrue the total number of steps to the goal, exactly, and then stop accruing once I'm at the goal. Is that good? Yeah? Which sort of answers my other question, right? So this thing is only going to be a meaningful quantity if it ultimately converges, which means I have to be able to get to the goal. If there was something if there was no path to the goal, then this thing is going to accrue cost forever, and my formulation was poorly chosen, right? Same thing with this. If I'm able to get to the goal and my control action is 0 at the goal, then my integral converges. But if the system is not controllable to the goal, then that's going to be unbounded, right? in these particular cases, everything's controllable, you can get to the goal, so this is okay. Okay, so the dynamic programming algorithm is in the graph search form is very simple, but it turns out that one can spend your life trying to come up with better algorithms to solve it in the more general cases, especially in the continuous high-dimensional cases. Doing approximate dynamic programming is a major theme going forward. So in the simple case here, where we just have all of our states, we have a moderately sized graph, then we're going to exploit that additive structure. Maybe I'll even do a little bit more right here. This additive structure gives me a recursive form. So for all I, let me say the JSI. I'll call it the optimal J. Use this for optimal. And this is cost to go. It's the min over the A's I'm going to take in the future of that cost. Given I start in some state SI, and I take the best possible actions I make the optimal decisions. It's the cost I'm going to accrue, right? It's my cost function. And the great thing about this additive form is that I can write this again. So this is a really gross thing to have to search over, right? If I have to search over all possible A's on this step, on the next step, on the other, every possible permutation of control actions, that would be a nightmare. But it turns out I can write this whole thing recursively as the min over a single A of taking one step. Right, this is my one-step cost. And that took my searching over all possible A's into the future into searching over just a single time step. And that's suddenly very tractable. Okay, so this is the standard famous dynamic programming recursion. It's actually what it is it's an equation that certifies optimality, right? So when you see this, you say that if you have a controller, if I have a controller that I want to convince you is optimal for this additive cost function, I can do that by providing the cost to go function, and you would then check, does it satisfy this equation? Does J equal min over A G of SA plus J star, right? If it does, then I've certified that that's the that cost to go function is an optimal cost to go function, and then my optimal policy is just the arg min over A. It's the A that minimized this, right? If I've given you a policy and a cost to go function, then you can certify that it's optimal. It's just a check, okay? But it turns out to be way more than that. So I don't know who did it first, but someone just said, okay, what if I just, I mean, I guess Bellman's the most famous for it, but, right, so what if I just took this equation and used it as an iteration? What if I said, I'm going to just guess a j hat. And I'd like to, so hat is my shorthand for guess, or approximation. And I'm trying to approximate the optimal j. And let's say I'll just start it off as initialize it with random numbers or zeros, you pick, okay? And then I'm going to apply this equation as an update. So I'll say for all I, j star si, I'm going to update it using this min over a g of si a plus my current approximation. Right, I'm going to just use my guess at the cost to go to update my guess at the cost to go. This is often, the language is a little funny. This is often called value iteration. Or people just call it dynamic programming. Iteration. I tend to use this especially in the infinite horizon case, because there's another term that comes in if you have a finite time that DP addresses. Okay. So this, you understand this is how you type this algorithm in, right? So you only have a finite list of states, so this is a finite set of numbers that represent this function, right? You can put it in a vector, and you're just going to update the vector like that, with that algorithm, okay? Here's the amazing thing. Even if you initialize this at random, it's guaranteed to converge to the optimal cost to go. Okay, there's a nice proof in Bertzikas or in many places that this update is a contraction mapping. It actually converges, and the unique solution is J star. Okay, it's actually even better than that. You can do it in batch or asynchronous, right? So if you, the way you'd think you'd want to do that is you'd go through and you'd make a copy. You know, remember your J hat, use that to compute updates for every state in my graph. You know, now update J, do it for every state in my graph, update, right, go back. If you're less careful than that, you just say, oh, I'll update this edge, and then this edge, and then this edge, and then this edge. Of course, you have to visit every edge infinitely often eventually, right? So you can't leave some edges out, then that it wouldn't converge. But under very mild conditions, even the asynchronous version of this converges to the optimal policy. Yeah?
You still need to initialize J hat goal states with the right cost function, right?
It actually takes care of itself. So you have to define what happens even in the goal state. So if there's a self transition, for instance, and then it'll take care of itself. Yeah. And the asynchronous version is cool for distributed algorithms, right? If you've got maybe a ridiculously big graph and you want to distribute it across multiple workstations, for instance, and they're all updating weights, as long as they share some amount of information, you can converge on the optimal policy still. Okay, so that's just a simple graph search algorithm, yeah.
What's the assumptions that have to be met in order for that to converge?
Additive costs is, so
there has to be something like with the time step has to be small enough to approximate continuity, right?
it's going to converge to the optimal solution for the discrete problem.
Oh, okay.
And I have not said anything about how well it converges to the solution of the optimal problem, of the continuous problem. You're right, there's a gap there. And it's a pain, that gap. And in fact, it'll never go away. Or not, I haven't made it go away yet. So this is just optimal for the discrete problem. Good call. Yeah.
Is there a way to know how quickly it will converge?
There are lots of things known about it. I think that, so let's see, there's a basic result. The fundamental result of it being a contraction mapping doesn't actually, to my knowledge, give the rate of convergence in a general way. But there's a lot of knowledge that people have about how to make it work faster, which I think is somewhat disconnected from that theory. So for instance, in the case where you have a shortest path problem with a goal, then you're better off solving everything from the goal, and you basically don't even need to bother updating the cost far from the goal in the initial passes. Now, I'll actually show some animations of it working, and it'll make that crystal clear. But there are sweeping algorithms that will do this in certain orders that they call prioritized sweeping, that will then have a much faster convergence rate. So I think there's a lot of algorithmic work that improves it in practice. I don't know of a great bound. It might exist. I mean, but the contraction metric, I think it just says it's less. The proof I know is just saying it's going to contract. Yeah. Okay, so this is just a little bit of algebra, but what I wanted to do is give you a lot of intuition, because this really is. This tells you something really important and magical about dynamical systems, even the pendulum, and even humanoid robots. Okay, if you could solve this iteration, and if you could watch it being solved, you would somehow understand more about the system. Okay, so let's do it for in a couple graphical places here. So the simplest sort of graphical illustration of this is on a grid, an actual grid world problem. And this is really simple, so I just won't spend much time. But imagine you're a trash can robot that lives on a 2D grid, right? Right, so you're a little trash can robot, or whatever. You can go up, down, left, right, or not move at all on this grid. And you've got some starting state, maybe, and you've got some goal state. And maybe there's some pit of despair here that you don't want to fall in. Right, so the way that the dynamic programming algorithm is going to work, let's say I started my J as 0 everywhere, and I'm going to just use 1 as my cost, so I'll do the minimum time. Then it starts off 0 everywhere. After one pass of the algorithm, it's going to go and put 1s here, but still 0 everywhere else, right? On the second pass of the algorithm, if I sweep through every state and update it, I'll figure out that this is 2 away from the goal, right? On the third pass from the algorithm, I'll figure out my 3s, right? I missed that one in a second, right? And I'll slowly propagate out a solution that tells me how far I am from the goal in terms of distance, right? The policy then, once I have that, is just a map that tells me go downhill in cost. From where I am, pick the direction that takes me down in cost, right? So a couple things to observe immediately is that, first of all, the optimal cost to go is unique. There's always some number which will get me, there's the right answer, there's no less cost I can get to the goal. The optimal policy is not unique. In many problems, it's not unique. For instance, here, I could go this way first or this way first. In both cases, I'll get to the goal. And that's true in general. That's true for more complicated systems. Also, optimal cost to go is unique. Okay. If I wanted to add into my cost function something that says don't go in the pit, then you could just somehow rule that out and not put edges in there, or you could put just really high cost. You could say maybe my cost of being in here is 100, right? And then the DP algorithm will never choose to step inside that, so it'll work its way right around it, right? And eventually you'll have a map across the entire grid. Now if I have a different, if I have different cost functions, if I somehow penalize the quadratic distance from this, right? If I had my quadratic cost, I could solve that too, and I'll just run the animations. Because what I want you to see is this growing of the cost to go as a way of sort of understanding the dynamics of the system. Am I 2 or 1? Okay, so this is a cost to go solution for a system that has a goal here, I think, and the pit of despair right here. And here you go. You see the optimal cost to go. This is the colors are changing as the total cost goes up. It changes color, okay, but it's going to just ooze out and slowly converge on the optimal cost to go, right? And avoid the obstacles. And even if it were to find yourself, if someone initialized you in that pit, they would get out of there as fast as possible and then go, right? And that's just a very simple but I think beautiful illustration. If you put different pits around or different goals around or whatever, then you could just watch the dynamics sort of ooze across that state. And I want to show you that same thing happening now for the double integrator, and then even for the pendulum, okay? Any questions on that? So what's going to look like for the double integrator here? So. First of all, the code's pretty simple. I define a little double integrator, and then I set up my dynamic programming problem. I've got two cost functions typed in here. One is exactly what we just said, which is that if I'm at the goal, return 0, otherwise return 1. That's my minimum time cost. And then most of this is just plotting. Almost all of that is just plotting, because in here I just run value iteration. Okay? Let's see what that does. Nice. This is what I get for changing it right before lecture here, but I know what I did. If I can find it. times 10. Well, let me do it for the other one here, which is what I tested. Okay, so this is the dynamics of this is what I would say is graph search, understanding the dynamics of the double integrator, okay? So the cost to go function of the double integrator takes this beautiful form, okay? We'll understand that exactly. It's gonna, if there was no saturations, then this would be a quadratic function, turns out, is the analytical solution for the quadratic cost. Okay, and the optimal controller is actually a simple linear function of Q and Q dot, okay? But there's some edge effects, first of all, because I didn't let my graph go too far. And so there's a little bit of a boundary effect here, okay? And there's some clipping because there's a total saturation on the control input U, okay? But this is just a dense graph on top of the state space of the double integrator. I really want to have this one work again. Okay. All right, now I'll switch it to the minimum time cost function. It's a kind of a funky cost to go, okay? But it's just oozing itself out, sort of uncovering the complicated long-term dynamics of the double integrator. Okay, it looks a little quadratic in the middle, but it's actually more complicated than that. It has this kind of trough, see? And here's maybe the punchline, right? What does it look like in the policy? What's the optimal policy? It's discretized, right? Because I have the graph. But isn't that, let's see if I was clever enough to leave it. Isn't that this, right? Just comes right out of the algorithm, right? So what is this, if we did the same thing now for the pendulum? I claim that the pendulum is actually pretty tricky, right? You have to swing up and balance. You want to pump, just the right amount of time so you get there as fast as possible. You're probably going to ride on your actuator limit most of the time. But the places in state space where you'd cut from going from one direction to the other are subtle, real subtle, right? So, for instance, there's a state right here near the top where I have enough control, I'm just going to go straight to the top. But there's a neighboring state where I got to go all the way around to get it, right? So what is that going to look like in state space? It's just changing the edges in my graph, running exactly the same algorithm. We should be able to find out, right? By the way, if I didn't have this plotting all these things, it would be basically instantaneous. All the time is being spent drawing these figures for us. Okay, so it swung up to the top. That was exciting. The cost to go function looks sort of beautiful, but definitely more complex than the last one. Okay, and what does the optimal policy look like? Well, it's bang bang up to the numerics. That one's going to drive me crazy. Yes, it swings up from lots of initial conditions, but here we go, right? So makes me wish I had done a few more grid elements, but still. So there's this line of places where you can, let me see if I can just up that a little bit. Okay, here's a quick approximation of the optimal controller, minimum time optimal controller for the pendulum, right? So there's this line where I'm going to ride myself into the goal, where I'm already at high energy on the eyeball. Kind of have an eyeball up here. For places where I'm here, I'm going to ride myself right into the goal, so I'm plotting that here, because I wanted to put the fixed point in the middle. So I'm going to ride that one directly in, okay? This one over here is all going to go, trying to go all the way around. And then I've got a different thing happening in the blue, right? And the reason for that, maybe you can even see it a little bit better here, is that there's a lot of places where I'm low cost, okay? Where I'm sort of close to the goal. I'm in this trough here, right? So this is, you can see the eyeball. Can you see the eyeball, right? That, I didn't type in the global vector field of the pendulum. I just told that there's a few edges or whatever here. And it basically discovered this eyeball structure, right? And what it's saying is that there's a channel of stuff here which is close to the goal. It's low cost to go, right? Minimum time. Blue is, this thing's close to the goal. This is really far from the goal, right? And then everything in between. And it's doing that by solving this back, realizing to go here, you know, I actually have to go all the way around in order to get here. And so, you know, these places are high cost. This is really high cost maybe because, basically because it doesn't understand that I have a finite discretization. So it's smacking into this velocity limit. And so that red right here is a little bit artificially high. But it should be high, but it's maybe not quite as high as that. Okay, but it just figured out the dynamics of my pendulum, right? And then you can see now maybe on top of that the bang bang policy that has to be. And it similarly has this, the eyeball is visible right there, right? Okay, if you do it for a quadratic cost, you can play with this, and it's all in the notes, so you can do whatever you like with this, but we can just solve that again for the quadratic version. What would you expect it to be if I change from the minimum time to the quadratic? You'd like it to not be living at the rails quite as much. I'm going to put a penalty on U. So you'd expect it to be less bang bang. Although there's still limits to there are still saturations. I have to have saturations because I've discretized U. Okay? But you generally expect it to be a little softer, a little smoother everywhere, depending on how big U is. Okay? That one still looks pretty tight, so why don't I crank up the relative cost on U.
I think you're using the other cost function right now. But if you look at the if,
Yeah.
if it's true,
Oh, shoot. Thank you. Yeah, that worked. Now I have I'm not as saturated. right? So this is my controller, and it's goes high, but it's actually fairly low other places. And this, I just think this is so beautiful. Look at that. It's figuring things out, right? Slowly realizing that all those states have to go all the way to the goal, right? Those are the farthest ones from the goal. And then it's converged. That's the one that's at the origin here. That was the one that took the longest to converge, right? Just like you'd expect. It's oozing itself out from the goal. But not in the Cartesian distance, but somehow in the dynamic distance of having to wrap itself around and understand the long-term dynamics of the pendulum. Okay? All right, so we're going to be able to do tons of stuff with this, but I also want to admit right up front that most of the course is required because this isn't going to work for more complicated systems, right? Why doesn't it work? Where do you hit the bottlenecks? There's a couple big ones, right? One of them actually is this accuracy point. That Nick brought up. Right, so we have some discretization error. Now, I think if some of you out there are like experts in PDE solving and sort of numerical analysis for PDEs, then you could do way better than what I've typed in here. But actually, I still think it's hard, probably. Maybe I just don't know enough PDEs, but because these are discontinuous in general. The policy, for instance, you saw those big ridges in the solution, and that's going to make numerics pretty hard. And in general, I think there's a lack of theory about how do you bound the error of my PDE solution. Because this is ultimately, you'll see more explicitly in the next equation, this is solving a partial differential equation over the space. Scale, it's, the cursive dimensionality is the biggest one. If I have to tile my state space, then that's okay in 2 dimensions. It's okay 4 dimensions. 6 dimensions, you're kind of pushing it, and 7's kind of right out. Unless you're just going to, you have an exponential cost in the number of states you'd have to fill in, and in practice, 10 years ago it was 5, and now it's maybe 6, but it's not going to 7 anytime soon, right? So this is not going to work for more complicated systems like that. But there's actually a bigger one, maybe the deeper one, that I want to call out even now. And that is that this is assuming that you know your model. Although this formulation you can put uncertainty in, and it's not too hard. But moreover, it assumes you can measure your state and take an action based on your current state. And that one is going to be a painful one going forward. So, if I'm going to manipulate, if I'm going to button up my shirt, right? I don't want to have to know the state of my shirt in order to button my, do my buttons. There's something just wrong about that, right? If I'm reaching into my pocket for my keys, I shouldn't have to know what Way's shirt is doing, right? In order to, there's something sort of broken about having to know every piece of your state in order to make an optimal decision. And that idea is just not going to scale. So we'll try to address that more in the future too. But in terms of our first algorithm that lays the mathematical foundation and gives us the intuition, this is awesome. And you can actually solve meaningful problems with it. People still use this in real applications. Okay, we'll do the continuous time versions on Thursday. See you then.